Good afternoon. My name is Dorota Lembrer and I am the YERMI representative for young researchers. This plenary is a lecture as a part of YESS10 Spring School, which has been organized online on April 25th to April 26, 2020. The first plenary lecture is given by Angelika Bikner-Ahsbahs. She is professor of the didactics of mathematics at the University of Bremen in Germany. Angelika's interests cover general questions on the epistemology in the scientific discipline of mathematics education, as well as specific questions on the epistemology of concrete processes of teaching and learning of mathematics and professional development of mathematics teachers. She has been engaged in activities for young researchers for many years and is the expert in the thematic working group 7 at YESS Summer School. She also led working and discussions groups at the last YERMI Day in 2019 in Utrecht. Angelika has been engaged in working and supervising of young researchers for many years. Very welcome to Angelika's lecture. The title of the lecture is Emergent Tasks, a story about how a theory-driven idea became a practical tool. Very welcome to all participants in this plenary lectures. Angelika, the floor is yours.
So, thank you for this nice introduction. I will talk about a specific phenomenon and later a specific tool, that is the emergent task. And I will tell a story about how this theory-driven idea became a practical tool. I will begin this storytelling with the context of discovery. The context of discovery was addressed in a situation where I wanted to find out how students can be supported in their interest development. So the starting problem was, how can interest in learning mathematics be supported and sustained in ordinary mathematics classrooms? So, my story plot consists of 5 steps. I will first show a model on interest development, then turn to the theory of interest and situation, which is a local theory on supporting interest of mathematics in the classroom. And then I will show how we found emergent tasks when we investigated interest and situation. These tasks were then explored, and finally they were implemented into a program for pre-service teacher education. So I will begin with describing a model on interest development. Interest development starts with catching interest by specific interest fostering situational conditions. But catch interest need not be held. It can be held when the students become deeply involved into meaningful activities at stage 3. If they repeatedly experience this interest, it can become more stable and develop into a part of the self as sustained personal interest. Stage 2 is important for fostering interest in the classroom, since it provides the bridge to personal interest, and it is a state in which students are deeply engaged into the mathematical activity. Normally, personal interest seldom occurs in the classroom. but lessons can be arranged so that all students have the chance to learn mathematics with situational interest. Already in 1993, Mitchell has stressed this point for the mathematics classroom. Well, the question was now, how are situations in mathematics classes shaped that might foster holding situational interest? Well, this question was answered by Willems. Willems found that cognitive activation, the cognitively activating environment, is the activating environment that most likely will support the development of situational interest. Interest in class is more than just an individual situation. Interest in the classroom that is fostered by the teacher and by the environmental environment addresses the whole classroom and not a single situation. Therefore, cognitive psychology, as used by Willems, is not really the approach that would allow us develop instructional concepts for fostering interest in mathematics. As we were looking in the classroom, we needed a collective concept, not an individual one. Therefore, we changed the background theory. We used a constructivist approach that is symbolic interactionism which is situated in the area of interpretive research in the classroom. This allowed us to reconstruct the students' views on mathematics in the classroom, and it showed how the methodological approach can be done. The theory of social interactionism is based on 5 features. The first one is that people act towards things like mathematical concepts according to the meanings they have about these things. And these meanings emerge from social interaction. That means interaction with peers in the classroom. And these meanings may also change according to interpretation in these social interaction. That means the way the students act in the classroom depends on the social interactions and their interpretations of the meanings they meet and the social interactions they observe. And this interpretive approach holds also for the methodology, and therefore research consists of reinterpretations of the interpretations of the students represented in the data. Our research aim now was to build a local theory, a foreground theory on interest development, of how interest can be fostered and sustained in the classroom. So the topic was to investigate situations which most likely show how classes who are interested are shaped in the mathematics environment. So this was the starting point to develop a more focused theory that addresses interest directly in mathematics and that goes beyond cognitive approaches in order to include the whole classroom as a collective entity. By investigating about 90 situations in the classroom, we could identify what we call interest-dense situations. Interest-dense situations describe a situations in the classroom or in the class where a problem is solved or a mathematical question is answered. Interest-dense situation can be identified by 3 features: involvement, the positive involvement of the students and the teacher, the positive dynamic of the epistemic process, and the way the students value the activity and the mathematics at hand. To go more deeper into the details, involvement shapes involvement in such a classroom is shaped in a specific way. Students and teachers focus on the student's line of thought independently from the content-specific expectations of the teacher. With respect to the dynamic of the epistemic process, we can say that in-depth insight leading to structure seeing is achieved through 2 epistemic actions: gathering and connecting mathematical meanings. And finally, value attribution is built on a didactic contract. The students value highly mathematical ideas or the production of mathematical ideas, and the teacher, on the other side, they assist the students to achieve these ideas. These interest-dense situations were then investigated, and they showed a problem. And the problem was that we could not explain how interest-dense situations were maintained. And this question led to the identification of the Emergent Tasks as a specific tool that may maintain interest-dense situation. The starting point was that we could observe that there were some interest-dense situations which were very short, up to 5 minutes. But there were other interest-dense situations which lasted several lessons. And we could not explain how these long-lasting interest-dense situations were maintained. What we did, we shifted our attention from the interaction of the students to the teacher behavior, because we thought that it is the teacher behavior who assisted to solve our problem. By doing this, the previous foreground theory of interest-dense situation now became a background theory within which we investigated the teacher behavior. We started our investigation by looking at how students solved several tasks. By doing this, we found specific tasks which started to become interest-dense, and later this interest density was somehow blocked. I will start with one such task to show what sometimes happens in a specific situation. In a classroom, in a class of grade 6, the teacher asked, how can you find 1/3 of a slip of paper? All the students got slips of paper and they started folding the paper. And Mira, for example, folded her paper once. She got 2 parts And then she folded each part into 2 again, and she got 4 parts. And finally, she said we can throw away one of them. Then we have 3 parts, and the situation is solved. The teacher was skeptical because throwing away was not a thing he wanted the students to do. And so another student took up the chance. It was Eric. And he said we could take up 1 part and repeat this procedure again. Divide it into 4 parts and throw one of them away. And other students said, well, this could be done with another part again and again. But throwing away a part was not accepted by the teacher. And so he blocked the situation up and showed what he had expected. So let's look first at what the students did. This shows the folding process of the students. What the teacher has expected was that the students made a spiral of 3 layers and then pressed these 3 layers upon each other. And then he expected the students to show 1/3 of the whole slip of paper. What we observe in this situation is that the students gather and collect mathematical meanings. They connect what they have done and get more and more and deeper involved into the process. But the teacher blocked this process all of a sudden with showing his own expectation. So let us look at what the students did. They were deeply involved in the activity and began to build an epistemic process that the teacher broke up. What can we learn from this process? Maya has proposed to do a value-added analysis. In our case, this means that the teacher could have given a redirected task which takes the ideas of the students up. So what we here see is the folding process, and the task of the teacher could have been take slips of paper, fold them the way described. How can you explain to find 1/3? The students could have cut the parts and put them together, rearranging them, thus observing that 1/3 is achieved in the rest, and the rest of it, the last part, converges to 0. What we observe here is a specific kind of solution of the general problem that begins by folding the paper into the slip of paper into 4 parts. It shows or refers to a power series of 1/4 to the power of n, whose sums converge to 1/3, illustrated by the folding process, of course in an empirical way. By rearranging all these parts, the students themselves could have observed this, how this worked, and could also have observed that the rest, the final or the rest part becomes smaller and smaller and converges to 0, leading to a distribution of the whole slip of paper into 3 parts, where one of them finally approaches to 1/3. 1 week later, students were supposed to divide 2 pieces of licorice into 3 equal parts. One group looked at the circular cross-section of the sticks of licorice that the students wanted to use. A discussion was going on how the circle can be divided into 3 equal parts. Neither fractions were known nor measuring angles. The students realized that they needed to know the center, but did not know how to find it. And so a whole and intense discussion took place about how the students could find the center of the circle. We just have a look into this discussion at a specific situation. Rachel all of a sudden says, Mr. Kramer, that is her teacher, once more a stupid question. How does one get the central point? How did they get it, the group, because that is so small? And another student said, that is just, and he wanted to say what I wanted to say. The teacher answers, yes, that's a problem, right? That's a practical problem. Oh no, how does one even find the central point in such a small circle? Right, exactly. Those are questions. And again, the students became involved in the question how to solve the problem that Rachel was put on the table. Finally, at the end of the lesson, the teacher posed a homework. And this was the homework in line 164. So first draw a circle, then act as if one wouldn't have the central point. One cannot find it anymore. And then how can one find it again? And when one has it, how can one divide this circle into thirds? Well, this subsequent two lessons showed interest-dense situation. The students came back from home with several ideas. 20 of 27 students had solutions. And these solutions could approximately be divided into 5 different kinds of methods for finding the center of a circle. 2 examples are shown next. In the first example, the students used a set square to find the maximal chord so that the central point is marked by 0. The second example, the students used 2 parallel rulers between the circle. The midth between the 2 touching points is the center. So during the lesson, the students were presenting their ideas, they were questioning other ideas, they used them and they checked them by trying whether the method was able to find the circle. Finally, they were expanding their knowledge, the methods, and applying the methods to new circles. And finally, their ideas and the 5 methods were institutionalized and later taken up. So, the teacher in this case was able to hold interest by a specific task, and that was the homework task, and this task was the emergent task. What we have identified by comparing the first situation with the last one, and we had several situations of the similar kind, situation where the interest-dense situation broke up, and situation where the teacher was able to maintain the interest-dense situation. So now we can define what an interest-dense or what an emergent task is made of. When a teacher conceives the mathematical potential of a learning opportunity and translates it into a task so that students' interest is taken up, expressed as an epistemic need, and secondly, acute problems are addressed adaptively, because this is exactly what the teacher did when he posed the homework. So, as we have identified the emergent task, we had a conjecture. We had a conjecture that these kinds of tasks maintain interest-dense situation in mathematics lessons. And so we explored these emergent tasks by looking at interest-dense situation of the data we had. First of all, we could distinguish between 4 different kinds of tasks according with respect to the 2 features. The first features that students express interest, and the second feature that the teacher formulates an adaptive task for a specific situation. Prepared tasks often do not address the 2 features. Sometimes they do by chance, but this is normally not the case. Spontaneous tasks often are posed by the teacher in an adaptive way, but according to his own view, not taking up what the students express as their interest. Then we found missed emergent tasks. Missed emergent tasks where the students express interest, but the teacher does not formulate an adaptive task. This is a task that appeared in our first example. And then the emergent task, which is the only kind of task that take up both aspects. So Sina Vogt has investigated all the interest-dense situation that we had, and she came to the following result. Emergent tasks entail further emergent tasks, which means that when the students express interest and they get a task which foster their interest, they often come to a new question and a new kind of interest, which requires a new emergent task. And so with one emergent task, we result in a whole series or sequence of emergent tasks. Often these emergent tasks are nested, and in most cases, they are tools to maintain interest-dense situation. Finally, we wanted to know whether these emergent tasks also appear in normal classrooms. And so Sina Vogt went to schools and has chosen randomly 10 lessons which she observed and tried to find out whether she could identify any emergent task. She could not find any. And so, as interest-dense situation, also emergent task is a kind of very rare phenomenon. So, as we have identified these emergent tasks, and we could explain how emergent tasks are able to maintain interest-dense situation, we also became aware that our emergent task reacts to a specific didactical problem, and that is how to teach in an adaptive way. So tasks designed beforehand, before the lesson, may cause a gap between teacher intention and students' mathematical activities. An emergent task could probably be a tool to close this gap. And secondly, optimal learning needs teacher intervention, transforming the learning potential into fruitful epistemic situations. And this problem can also be solved by using emergent tasks as a teaching tool. We now come to the final situation where we implemented Emergent Tasks as tools for pre-service teacher education into the study program. This began with a specific project in which we wanted to develop a model for inclusive teaching in the mathematics classroom. This project was supported by the German Telekom Foundation, and the aim was, as I said, to develop a concept for teaching an inclusive classroom, but together with teacher students. And the question was, how can the epistemic processes be adapted to the students' need in such an inclusive classroom? And the methodology was a double design process. A design process on the university level as well as on the school level. Within 3 years, we developed a concept of such a kind of teaching together with the teacher student. This concept began with using ideas about differentiating in the planning differentiating tasks in the planning according to a central mathematical idea. For example, measuring the area. In addition, we took an idea from management research to shape the classroom in a way so that all the students could participate in the mathematical activity. It was sense-making through storytelling. And we invented mathematical stories to allow participating of all the students. Finally, we used Emergent Tasks because they could take care that every student does not only participate in the classroom, but has also the chance to make progress. And so these three features were developed together with the pre-service teacher students in their practical experience. It began in a specific situation that we identified Emergent Tasks as a helpful tool for teaching an inclusive classroom. In a classroom or in a class of grade 5, where the students were supposed to learn about measuring area, Maya has discovered a specific idea. So she said, if the around of an area, that is the perimeter, is large, the area cannot be small, she said. This, of course, is not true, but we analyzed the whole situation and reflected on the situation together with the pre-service teacher students, and we thought that Emergent Tasks for such a situation could be a good idea to be taken up and revise the lesson for the teaching of the same situation in another class. And indeed, the same situation appeared again. What we had prepared was a specific kind of Emergent Task. It was the task to take this shoestring and investigate for us whether a large way to go around always leads to a large area. And By taking up the shoestring, all the students could experience that the perimeter can be the same, but the size of the area can be different. And by this very simple tool, all the students in the classroom could finally distinguish between the two concepts, the perimeter and the area. Well, we then implemented the idea of emergent task into the study program. And this was done in 3 steps. The first step was using vignettes. Vignettes as shown in the example before. If the round of an area is large, the area cannot be small. The question to the teacher students was then, how can you as a teacher take up the student's idea or interest in a task for overcoming barriers? The second step was building a focus group. Focus groups of 2 to 3 students who teach the same lesson in 2 parallel classes, while the first lesson is reflected and revised in order to increase learning opportunities for emergent tasks in the second one. And the third step was that the students were supposed to explore and collect emergent tasks and finally write a report. I will now give an example about one emergent task that appeared in such a report. What you observe here is a slide where a standard parabola is shifted 4 units up and 4 units down. And the students in this class were in grade 8, and they worked on functions, on quadratic functions. And one student observed that these 3 curves somehow approach each other, that the distance between these curves seem to be narrowing when the x value increases. And one student said the parabolas do intersect somewhere because one approaches more and more the others. This is of course not true because all the 3 parabolas have the same shape and they are just shifted, and so they cannot intersect. So what kind of emergent tasks did the students pose to these students who have observed such a feature? The first emergent task was giving a transparent with a standard parabola, and they said, I gave the task to check your conjecture with this transparent. What do you observe? And the second emergent task was compare the distances of the ordinates at different x values. What happens? Rethink your conjecture. The first emergent task addressed the function as an object, and the second emergent task addressed the function as a correspondence of x values to the ordinates. So I will now show you 2 statements that came up in our oral evaluation. The question for me was how the teacher students observe the emergent tasks, what they think of them, whether they use them only in one situation or in further situation. Rexa expressed the following. She said, emergent tasks are somehow absolutely normal because every good teacher uses them. So note that we could not identify any emergent task when Sina Vogt investigated and employed them in the real all-day and ordinary classroom situation. Ole, another teacher student, said, "I used stories and emergent tasks in chemistry. It worked as well." So an emergent task no longer was a theoretical construct, but a heuristic tool for adaptive teaching. And statements like the two were not just singular statements. Statements like these statements appeared again and again when we evaluated or we talked to the teacher students. So now let us recall the whole process of investigation. The process of investigation started with the original problem, how to support interest in math in the classroom. This resulted into a local theory of interest-dense situation, but it also pointed to a specific problem, how these situations can be maintained. And this led to the investigation of the solving processes of the students in the classroom. And from there, from the comparison of the different solving processes, we could identify emergent tasks, which could have been a candidate for how to maintain interest-dense situations. This was further investigated and justified. And finally, emergent tasks became one part of our instructional model for inclusive teaching. And as a final step, we implemented this model into pre-service teacher education, where the teacher used emergent tasks finally as a heuristic tool for teaching, which even could be transferred to another subject, such as chemistry. Thank you for listening.